Good morning, everyone. My name is Khushi from BSc Chemistry Honors, second year, and today the chapter is Epoxides. Introduction. Epoxides are cyclic ethers having three membered rings in which oxygen is one of the atoms. They are also known as alkene oxides or oxyrenes. The simplest epoxide is ethylene oxide. In the common system, epoxides are called as alkyne oxides. In the IUPAC system, they are named as alkene oxides, epoxy alkanes, or oxyrenes. The common and IUPAC names of some epoxides are given below: ethylene oxide, ethene oxide, epoxy ethane, oxyrene. The chemical behavior of epoxides is quite different from acyclic ethers. Synthesis of epoxides. First, epoxidation of alkenes. Epoxides are usually prepared by the reaction between an alkene and an organic peroxy acid, also known as peracid, RC double bond OH. The reaction is known as epoxidation, in which alkene plus peroxy acid epoxidation, which will give epoxide. Peroxy acids commonly used in the reaction are peroxyformic acid, peroxybenzoic acid, peroxyacetic acid, and chloroperoxybenzoic acid. When a solution of peroxy acid and alkene in ether or chloroform is allowed to stand, epoxide is formed. For example, 2-butene plus peroxybenzoic acid will give 2,3-dimethyl ethylene oxide. Cyclohexane plus peroxybenzoic acid will give cyclohexene oxide. 1,2-dimethyl hexene. It may be noted that epoxidation of alkenes is a stereospecific reaction in which the stereochemistry of the substituent on the double bond is maintained. Thus, a cis alkene gives a cis epoxide and a trans alkene will give a trans epoxide. The reagent most commonly employed for epoxidation of alkene these days is magnesium monoperoxythioate (MMP). Mechanism. The mechanism of epoxidation involves the transfer of an electrophilic oxygen atom from peroxy acid to alkene as depicted. Second, from halohydrines. When halohydrines prepared by reaction of aqueous solution of chlorine or bromine with alkenes are treated with a base, HX is eliminated to yield an epoxide. For example, when ethene plus Cl2 plus H2O will give ethylene chlorohydrin. And second reaction, ethylene chlorohydrin plus KOH, which is a strong base, will give ethylene oxide plus KCl plus water. Mechanism. The base attacks the halohydrin to abstract the hydrogen from OH part of halohydrin to form an alkoxide ion. The nucleophilic oxygen of the alkoxide ion displaces the halogen from the adjacent carbon atom to form the epoxide as shown. It may be seen that the reaction involves intramolecular, that is within the same molecule, nucleophilic substitution reaction and is therefore treated as intramolecular Williamson synthesis. It should be also noted that as in SN2 reactions, the attack of nucleophile takes place from the back side of CX bond. Third, manufacture of ethylene epoxide. Ethylene oxide. Ethylene oxide is manufactured by passing a mixture of ethylene and air under pressure over silver catalyst at 475 to 675 Kelvin. Chemical reactions of epoxides. In contrast to acyclic ethers, which are chemically quite inert, epoxides show high chemical reactivity. This is due to the highly strained nature of the three-membered ring system. Ring opening reactions of epoxide. In the three-membered ring containing oxygen, the CO-C bond angle and the C-CO bond angle are nearly 60 degrees each. This large distortion from the normal tetrahedral angle of 109.5 degree causes very large strain in the epoxide molecule. As a result, epoxide undergo a number of ring opening reactions quite easily, and these reactions takes place through the cleavage of one of the carbon oxygen bonds and may be either catalyzed by acids or brought about by bases or nucleophiles. Next, acid catalyzed ring opening. Just as simple ethers undergo cleavage of the molecule on reaction with acids, epoxide undergo ring cleavage on treatment with acid even under mild conditions. First, acid catalyzed hydrolysis. One of the most important cleavage reactions of epoxide is their hydrolysis to form 1,2 glycols. Hydrolysis takes place even in the presence of dilute mineral acid at room temperature. Epoxide plus water in the presence of acidic medium will give glycol. For example, ethylene oxide, which is CH2OCH2 plus H2O in acidic medium, will give CH2OH, ethane 1,2 diol, or simply we can say ethylene glycol. Second, acid catalyzed reaction with alcohols. For example, CH2OCH2 plus CH3CH2OH in the presence of H2SO4 will give CH3CH2OCH2CH2OH, which is 2-ethoxyethanol. Third, reaction with halogen acids. Epoxide react with HCl and HBr to form chloro and bromohydrines. For example, CH2OCH2 plus HBr will give CH2BrCH2OH, ethylene bromohydrine. Mechanism of acid catalyzed ring opening. The mechanism of acid catalyzed ring cleavage may be illustrated by considering the hydrolysis of epoxide. In the acid catalyzed hydrolysis of epoxide, the epoxide is initially protonated by the acid. The protonated epoxide then undergo nucleophilic attack SN2 by water to cause ring opening by breaking carbon-oxygen bond. The reaction is completely by the loss of a proton as depicted. Third, nucleophilic ring opening. Unlike simple ethers which don't undergo ring cleavage by a base or a nucleophile, cleavage of epoxide ring takes place even by such reagents due to the ring strain in the molecules. For example, when treated with OH negative ions at high temperature, epoxide ring gets cleavage to form 1,2 glycols. Ethylene, which is CH2OCH2 plus H2O in the presence of OH negative will give OHCH2CH2OH, which is ethane 1,2 diol or ethylene glycol. Mechanism of nucleophilic ring opening. The mechanism of nucleophilic ring opening is shown below with the help of basis hydrolysis of ethylene epoxide. The strongly nucleophilic hydroxide ion attacks the epoxide and displaces the oxygen atom from one carbon by SN2 reaction. The product thus formed gets protonated to form the glycol as depicted below. Orientation of ring opening. First, anti-addition. The ring opening of epoxide led to the formation of products corresponding to anti-addition to carbon-carbon double bond. For example, acid catalyzed hydrolysis of cyclopentene oxide yields trans 1,2 cyclopentane diol. Cyclopentene oxide, which is benzene ring O plus H2O, H positive will give trans 1,2 cyclopentene diol. Second, regioselectivity. Unsymmetrical oxyranes can undergo ring opening in two different ways and generally lead to different products in the acidic and basic media. In acidic medium, the nucleophile generally gets attached to the more substituted carbon, while in basic medium, the nucleophile becomes attached to less substituted carbon. CH3CCH3OCH2 plus CH3OH in presence of H positive will give CH3CCH3OCH3CH2OH, where nucleophile is CH3O negative gets attached to more substituted carbon and forms major product. Next, CH3C, CH3, CHO, CH2 plus CH3O negative in the presence of CH3OH will give CH3C, CH3COH, CH2O, CH3. Major product. Nucleophile gets attached to less substituted carbon. Explanation. The difference in regioselectivity in acidic and basic media may be justified as follows. In basic medium, the ring opening in an SN2 displacement by the nucleophile on the unprotonated oxirane, as in SN2 reactions, the attack takes place at the less substituted and less sterically hindered carbon. In acidic medium, the first step is the protonation of oxygen of the oxygen of the oxirane ring due to the electron releasing groups attached to the more substituted carbon. Positively charged oxygen attract the electron pairs of its bonds with this carbon to a greater extent than the electron pair of the bond with the less substituted carbon. As a result, the more substituted carbon oxygen bond becomes weaker than the less substituted carbon oxygen bond. Therefore, ring opening takes place preferably at the more substituted carbon oxygen bond, and the product contains the nucleophile attached to the more substituted carbon. The weaker bond is preferentially attacked by nucleophile. Other nucleophilic ring opening reactions. Reaction with Grignard reagent and organolithium reagents. Epoxide also undergo nucleophilic ring opening reactions with Grignard reagent and organolithium reagents. The product initially formed on hydrolysis yields a primarily alcohol containing large number of carbon atoms. The epoxide generally used in this reaction is ethylene oxide, and the alcohol formed contains 2 carbon atoms more than in the Grignard reagent. For example, CH3CH2CH2 MgBr, which is N-propyl magnesium bromide plus CH2OCH2 in presence of ether, will give CH3CH2CH2CH2CH2O MgBr. In the presence of H3O positive, it will give CH3CH2CH2CH2CH2OH plus MgOHBr, which is 1-pentanol plus MgOHBr. And second reaction is CH3CH2CH2CH2Li and butyl lithium plus CH2OCH2 in presence of ether will give CH3CH2CH2CH2CH2CH2OLi. In presence of H3O positive, it will give CH3CH2CH2CH2CH2CH2OH plus 1-hexanol plus LiOH. Reaction with alcohols. CH2OCH2 plus CH3OH in presence of CH3O Na positive will give CH2OH CH2OCH3, which is 2-methoxy-1-ethanol. Reaction with ammonia. CH2OCH2 plus NH3 will give OHCH2CH2NH2, which is 2-amino-1-ethanol. Fourth, reaction with hydrogen cyanide. CH2OCH2 plus HCN in presence of H2O will give CH2OH CH2CN, ethylene cyanohydrine. Fifth, reduction with LiAlH4. 4CH2OCH2 plus LiAlH4 will give CH2H CH2O Al negative L positive. In the presence of 2H2O, it will give 4CH3CH2OH LiAlO2. Problem. Write the formula and name of products following reactions. The products are, for first reaction is trans 1,2 hexanediol and propylene 1,2 cyclohydrin. Thank you. That's all about this chapter.